that's the 20% cell. And I have to follow this tilted axis for this circle. And I do the 30% clay. Clay is the horizontal axis. And then the three of them, they intersect at this point. That belongs to sandy clay loam. So based on the percentages of sand silty clay, we use the soil texture triangle, all right? And then depending where they intersect and what polygon, I'm just reading off the soil texture that we have. Right? And if I'm not wrong, we have a 12 different soil texture classes. Okay, either 12 or 14. Let me count. 12. So we have 12 different texture classes. Okay? It is simple. Once we know what it means soil texture and how to use the triangle, it's not that complicated. That's why we like to assess this property. And not only because it's simple, but also we like to assess it because of its significance. So take a look at this equation now. Okay, and for this equation, you don't have options. You're just gonna type in your answer right away. Okay, so you're given a soil sample, you did some analysis, you figured out that you have 40% sand, 40% silt, and 20% clay. Figure out. Sand. I'm looking right here on the sand axis, that's the 40, and then I have to follow this axis representing the 40, and then I go to 40% cell. I have to follow this one, and then 20% clay, and then I have to follow this one. Alright, so I'll give you maybe another 10 seconds to submit your answers. Loam is a correct answer. I think there is a student intended to say loam here as well, so that's correct. Now, if you said it's not sand itself, and then in clay loam, you're fairly close, but this is actually in the loam texture. So if you follow the 40%, 40% and 20%, all of them they interact right here at the loam factor. And underline loam. This is I only need 2 of the percentages. Yes, that's a correct observation. So your classmate is asking me, like, practically, do we only need 2 percentages? Yes. If I have to, I figure out the third, and even right here, 2 of them, they're able to intersect at that point. Alright? So 2 or 3, if I have the percent sand, silty clay, or 2 of them, I'm able to figure it out. Now underline loam. Loam is the best, or is the best desired soil texture when it comes to soil fertility. Loam is the best soil texture when it comes to nutrients and water availability. Loam is the best texture when it comes to plant growth and performance. So typically we try to manage our soil, so if we end up with a texture that is not long, and we try to manage the soil to make it a long texture. We can add certain mixes, we can manage the soil, we can add sand, we can add silt. So we are pushing it in the direction to become a long texture. Now what happens if I have some percentages where they are at a boundary of a polygon? So if the percentages that I got, I landed right here. From this boundary, between long currently long. If that's the scenario, and I reported either one of them, you're correct. Correct? So if your point is at a boundary between two polygons, you just choose one, and no one can tell you no, it's wrong, it should be in the other place. It doesn't go like this. Yes. So the bold black line, this is the border between two points. And then you can notice that when we have a high percent of sand, if I look at this small triangle right here, the sand texture. Sand texture, it could be starting from 85% or higher. So if I have sand dominating 85% of the entire sample, I name the entire texture as sand. So we have, like this is the type of material you find in a desert ecosystem, warm desert ecosystem, or the sand that we find on beaches. Alright? So 85% or higher, right away we go with the soil, with the texture being actually sand. And then we have also silt texture. And it's the same idea. I have a dominance. So if I have a silt texture, it doesn't mean that it's entirely silt 100%. No, about 85% or higher, that's a silt texture. And also we have a clay texture on its own as well. Now, besides texture, what other physical property you access? This is what we call structure. By the way, to study soil, I should have mentioned this earlier. Anytime I want to study soil in the field, okay, this is the proper way to do it. All right? I have to excavate 1 meter of the soil profile. So my first activity, usually when I'm teaching the Geography 108, and that course is named Soil Property. So we do a field trip. We have a 1-day field trip, and we go study soil in the field. So the first activity I asked the student to help me with, we need to excavate a 1 meter by 1 meter deep soil pit. So it's a lot of excavation. So whenever I'm saying we're studying, looking at soil properties, studying soil properties in the field, assessing texture, that's something that's not going to be just visible to us if I'm walking on soil. Studying soil actually involves digging a soil bed. Typical dimensions 1 meter, I should go 1 meter depth. Now whenever we try to do this activity here in Ottawa and in other parts of Canada, even when I was in Vancouver or Halifax, we never made it to the 1 meter depth. Sometimes we stop at 30 centimeter depth. If we're lucky, we manage to get to 60, 70 centimeter depth. Why? Yeah. We hit the lower layer, including bedrock, very early. Our soil in Canada, we will talk later about time as a factor of soil formation. Our soil in Canada is very young. It's only about 20,000 years old. on a soil formation time scale, that's considered juvenile, young soil. Why? Around the 20,000 years. Why I'm choosing this number? Do you remember what we had affecting the Little Ice Age? All of our landscapes were covered with glacial ice. They were burying the bedrock material, the landscape. So our soil profile, they started developing after the melting of ice 20,000 years ago. So that's why within 30 centimeters sometimes we had a layer where we cannot excavate anymore. Anyhow, so we did this activity, and now I'm looking at a cross-section of the soil profile, and I'm looking how that profile looks like, and I start noticing some geometrical shapes. This is common. And for us in Ottawa, when we do this activity, it's very common for us to find the prisms, columns, right? And to find the plates. So the second photo from the top. And usually when we have soil with high clay content, these two structures tend to develop. Our soil in Ottawa, we have high clay content in our soil. Now when we see this geometrical shape, this is what we call structure. Alright? So again, we have from the top, this is what we call a granular. So I have aggregates. I have the soil particles aggregated together in a random shape. That's the granular. But I have aggregates. And then we have the platey that looks like plates, layers, stacked on top of each other. And then we have the blocky blocks. And then between the blocks, you can notice the gap. This is pore space. Alright? And then I have the columnar or prismatic columns stacked next to each other. Now, what's nice about texture? Yeah, that's okay. Okay. So as long as you maintain the 1 meter by 1 meter, okay, you got to 30 centimeter. That's what this is your soil profile. But if we have a deeper soil profile, it's a 2 meter depth. It's enough for you to stop at 1 meter. If you want to study soil property, you want to examine a different aspect. Let's say you want to examine water infiltration, then maybe you need to get deeper. Now, what is the significance of texture? Whenever we have texturing, usually between these geometrical shapes, I have large pore space. And that large pore space allows water to infiltrate through the soil profile all the way to lower layers, all the way to get to the groundwater. So it facilitates drainage of water. And this is also of significance. I don't want the soil to get inundated with water. If all soil pore space is actually inundated with water, I have no space for gas anymore. All the organisms of the soil, they need to exchange gases with the soil air. Alright? So that's the significance of the structure. Structure is important to facilitate the drainage of water. So that's another soil physical property. It is a desired. So if I excavate the soil profile and I'm assessing the soil, that's a good indicator if I have a structure. Especially in soil with high clay content. Typically, soil with high clay content, we have the issue of water drainage. So the structure facilitates that process now. So here I have this question. I'm just checking with you guys your understanding of texture versus texture. Okay, so the starting part is texture. Texture refers to what? Versus structure refers to what? screwed up. I had the wrong format of the question. Just gonna. I have to redo it. I'm not able to track every single answer to that question. Okay, because you've already attempted the question and I already have most of the responses I'm expecting. I'm going to stop the question literally in another 5 seconds. Okay. So texture is particle size, distribution, and the structure is the aggregation of source particles into secondary particles. Okay. Soil color. Soil color is another soil physical property. Right? And it's very common for us to assess color, to look at color and to report color. Why? Because it can tell us about some of the soil properties, not all of them, but it's an indicator for some of the properties. Now, before I talk about color, I'm introducing one term here, which is humus. This is the very well decomposed organic matter that looks black or dark brown in color. So whenever we use the term humus, it's just I'm saying organic matter. Okay, if I want to be more accurate, very well decomposed organic matter. It's decomposed to the extent that I don't recognize the origin anymore. Now, color indicates composition and chemistry. Black soil or dark brown soil, what does it tell us about content? Organic matter, correct? Now what about red color or orange color or yellowish color soil? A lot of iron oxides, very good answer. Guys, you're familiar about when iron reacts with oxygen, we get the rusty color? Okay? So that's basically what's happening there. So we know that it has a high content of iron oxide. Now what about a white or a pale color? What does it indicate for us? Usually when we have a pale color, it means that it is rich in clay content, it's rich in silica or aluminum oxide. So see, now knowing color, which is a physical property, all right, of the soil, can tell me a little bit about the chemistry of the soil. And I'm not doing any sophisticated analysis, I'm just looking at the soil sample. Now, when we assess color and we need to report color, we use what we call the Munsell color chart. So it's a tiny booklet, and that tiny booklet, you see, it has different shades of colors and then reflect pages. And typically, we put a little bit of the soil sample on the tip of our finger, and you see how we have these holes, and then we try to put it behind the hole so that we have a very accurate visual comparison. Okay. And then when I want to report the soil color following the Munsell color chart, I have to report what we call the hue value chroma. What is the hue value chroma? So if you look right here on the very top of the page, the top right side of the page, I have a certain numerical, alphanumerical value. Sometimes 5YR, I flip that page, it's a different code. But basically this is telling me what is the color. It's Y for yellow, R for red. So it tells me overall what is the color. And then on the two sides of the same page, you see these numerical values, right? You see I have some values. And then right here we have also some values on the bottom axis at the bottom. Okay. So at the bottom, the horizontal axis, this is what we call chroma, and the vertical axis on the page, this is what we call value. So I'm simply by using this combination of hue, value, chroma, I'm telling the reader, if you grab the Munsell color chart, hue is telling them what page to open. Go to this page. And then within this page, I'm specifying the column and the row. By the value and chroma, from value and chroma, I define what column to intersect with what row, And this way, they know exactly which one I'm referring to. Okay. Now I'm done with soil physical properties, or I'm done with the properties that is based on the mineral fraction of the soil. Texture, structure, color. Structure and texture, they're only based on the mineral fraction. Color, I can apply it to mineral fraction or organic matter. Now I have only one slide about soil air, and then I'll spend the rest of the class time today talking about soil water. So first, we need to remember, I say on average, soil air is 25% of the soil sample. It's a dynamic percent of the volume. So if it's raining next day, and all the pore space is occupied with water, that percent can drop to 5% or less. And then if we are a drier period of the year, that percent can go to 35% or 30%. So the percent of soil air depends on how much water I have in the pore space. Importance, it is needed by organisms that are dwelling the soil. They need to exchange gases with the soil. And that's why typically soil air has a greater carbon dioxide and less oxygen as compared to atmospheric air. Because they uptake oxygen and they release carbon dioxide. But every now and then we have exchange between soil air and atmospheric air. Soil water. So water is an important, not unimportant, it's a crucial resource for plants. Plants, most of them, except the ones with very high adaptations to dry environments, like desert plants and so on, most of them, they need water to survive all the time. So where is the water kept? It's held in the pore space. So in between the solid particles of the soil, in between the mineral fraction of the soil. Now, one more time, the volume of water, the 25%, it depends on how much water is present. Wet period of the year versus dry period of the year. Flooding event versus a drying event, right? And size of pores. The bigger the pore size, the more water can stay or actually cannot stay. We will expand more on this particular sentence, can or cannot stay in the pore space. Now, when it comes to types of soil water, we differentiate between what we call gravitational water. And what is the gravitational water? This is the portion of the water that will be lost from the soil profile due to gravity. Gravity is able to pull down material, correct? Gravity attempts to pull down material towards the center of the earth. So the portion of the water in the pore space that the gravity can pull it down all the way to go below the soil profile, this is what we call gravitational water. We have another proportion of the soil water that actually resists gravity. It will stay there. It will stick to the soil particle. It will adhere to the soil particle. It will cling to the soil particle. This is what we call capillary water. So the soil might look dry for us, but still there is a little bit of water that is sticking to the soil particles. This is what we call capillary water. Now, in relation to capillary water, I will introduce the term storage capacity. Also, we call it field capacity. So, in some of my upcoming slides, you will notice we are using the term field capacity, same as storage capacity. So, what is the storage capacity? It's simply how much capillary water we have. It is how much capillary water we have and available for plant use. Now, storage capacity is a function of soil texture. Do you remember earlier I told you underline texture? And there was one sentence on my texture slide. Texture determines water and the nutrients availability. Okay. So this component here, storage capacity, is what we look at to start assessing water availability. Now, I have another part that relates to this. Storage capacity is a function or depends on the texture, and in more detail, we have highest storage capacity in fine texture. Can you give me an example of a fine texture? High clay. So remember we had a texture named clay. Okay. So when I'm thinking about fine texture, the extreme example of fine texture is the clay texture. And then any texture that has a clay as part of its name is also a fine texture. So let's take a look. I'll very quickly go back to the soil texture track. So this is the clay, and then I have sandy clay loam, I have sandy, no, this is the clay on the top, excuse me. This is the clay, sandy clay, clay loam, silty clay, right? So this is a fine texture, and anything around it, it is not as fine as the clay texture, but it's a close to it. So highest storage capacity is fine texture and or abundant organic matter. That's why organic matter is desired to be part of our soil sample. That's why whenever we're trying to improve our garden, we add organic matter. Correct? We go to any departmental store, Canadian Tire, we grab black soil or brown soil, dark brown soil. We're simply adding organic matter. Organic matter has a high water storage capacity. It stores water and makes them available to plants. Now, I'll go back to the idea of high storage capacity, fine texture plus abundant organic matter, and I will introduce another term, which is the wilting point in relation to that. So what is the wilting point? You know, this is when we're placing a plant in a pot or in a garden. Maybe water conditions are not favorable. The plant will wilt and die. That's what we mean by wilting point. Okay. So in the wilting point, we need to think about the critical water storage level needed by plants to survive. Below it, plants will wilt and die. Now, wilting point depends on texture as well. Fine texture has a very high wilting point. Remember clay has a fine texture? Clay has a high storage capacity. It means it's able to hold a lot of water, correct? But the clay has a very high wilting point. Because clay has a high wilting point, what it means that as soon as the storage capacity drops a tiny bit, plants will not survive there. All right? So there are two factors that I want to consider when I start thinking about plant availability, not the plant, water availability to plants. I need to consider storage capacity. I want to have high storage capacity, but I want to have the low wilting point. Because if I have a high storage capacity and a high wilting point, that's not very useful. Plants are not taking their need of water when we have a high wilting point. And if I have a low storage capacity, regardless of the wilting point, we don't have water at all with a low storage capacity. So that's a problem as well. So when I start thinking about water availability, not water storage, water availability is the amount of water stored that the plant can actually utilize. When I think about it, I want the soil texture to enable the storage of water, but also I want a low wilting point. So now how do we represent that graphically? Let's take a look at that graphical illustration. On this graphical illustration, I have the texture, coarse versus fine. So clay versus sand, and in the middle, something that is more balanced, the loam soil, loam texture. And then if I plot the storage capacity and the wilting point, look at the clay. At first, this is how this is the shape of the curve. The top one is the storage capacity or field capacity. Lower one, wilting point. I'm assessing a clay. Clay has a high field capacity and a high wilting point. How do I interpret it? Okay, this is similar to, I have a very rich family member. He has a lot of money, but he doesn't want to give me any money. And you know how expensive nowadays. You have to cover your expenses. That's not useful to me, correct? So there is a lot of water in the clay, but it's not releasing the water. High wilting point, it means it's not releasing the water. All the water is held very tightly by the clay particles. That's not helpful for us. Now sand, this is my other family member, who's very helpful, very supportive, wanna help me, but doesn't have any money to give me. That's sand. So sand wanna offer water, but doesn't have water to offer. That's not useful from plant perspective. Doesn't have water to offer. Even if it wanna release it, it's not there. Sand. Now, typically, when we're trying at this graph, I try to find the texture where I have the greatest distance between the two curves. So if you notice the loam texture right here, it has kinda moderate storage capacity. Storage capacity is not the greatest. Clay has a higher storage capacity. But also it has a relatively low wilting point. And then if you look at the space, the gap, the distance between the two curves, it is the greatest at the loam texture. So for me, how do I interpret this? Loam is the ideal texture when it comes to water availability. That distance between the two curves, field capacity versus wilting point, that distance separating them, it is a visual representation for water availability. Water can be uptaken by plants. So this is what I'm concerned with. Right? So I see it's the best in the loam texture. and I see the space between field capacity and melting point is minimal at either the sand or the clay texture. So I don't want my soil to have a sand texture. Plants will not get water because it's not there. I don't want my soil to have a clay texture. Plants will not get water. It's there, but the clay is not releasing it. And that's why we desire to have the loam texture, because it has a very good balance between water storage and the release of water, and that's what we call water availability. Another visual illustration. So same concept, but on this visual illustration, we have all different textural classes are listed there. So you can see from sand, fine sand, going through loam, and then finally going to clay. And then one more time, storage capacity versus wilting point. The greatest distance separating these two curves is at the loam texture. That's water availability. That's a desired texture for us. So the loam texture, because it has relatively high water storage capacity, relatively low wilting point, most stored water is available for plants. Now we will wrap it up and then we will move to start looking at nutrients available. Right. And whenever we start talking about the nutrients, can you give me an example of a nutrient for plants?
Nitrogen.
Have you ever, guys, you got a fertilizer, you're trying to add fertilizers? Yeah.
Nitrogen.
Nitrogen. What else? Nitrogen is one of the most important and crucial nutrients for a wide variety of plants. Now, when we talk about nitrogen, in what form do we provide it to plants? Any idea? Like we have nitrogen gas, correct? Are plants uptaking nitrogen gas? No, they don't. Otherwise, we don't have to add nitrogen as a fertilizer. Any idea in what form we add or plants can uptake nitrogen as a nutrient? It uptakes it in the form of
Solid.
in the form of ions. Okay. For instance, nitrate ion. Okay. Another ion would be ammonium ion. Can you give me another example of a solid nutrient? Yeah. Phosphorus. All right. They take it in the form of phosphate. Potassium. They take it in the form of a potassium ion, K+. Magnesium. Calcium, all of these nutrients, when we are listing them, you want to think about them in their ionic form. Alright? So potassium ion, magnesium ion, calcium ion, phosphorus phosphate, ammonium, nitrogen, nitrate. Alright? Now for these ions, to become ions, they need to dissolve in water. And through water, when the plants are uptaking water, they will uptake these ions. And this is where we introduce the term soil solution. What is soil solution? Soil solution is simply soil water with some ions dissolved in it. It is through the soil solutions that the plants uptake a nutrient. Plants cannot remove a nutrient from a soil directly. So the soil particle will release it to water, and the water will mediate the transfer of the nutrient to the plant. Now, this is not from chemistry. This is just from soil science as a discipline. Whenever I use the term bases versus acids in the context of the nutrients, so soil nutrients, we refer to them as bases. Alright? So examples of soil nutrients: calcium, magnesium, potassium, phosphate, nitrate, all of those, because they are nutrients, I call them bases. Now, any ions that are not the nutrients to the plant, such as hydrogen, aluminum, sodium, I refer to them as acids. I'm not talking about pH yet. This is terminology in the context of the nutrients of the soil. So any ion that is a nutrient, we refer to it as bases. Not a nutrient, hydrogen, aluminum, sodium, acids. Now let's take a look at this visual illustration. Okay. You see the brown two-layered structure? So the brown color two-layer structure, this is a visual representation of a colloid. Anyone recalls what are colloids? Colloids, they make up what? Clay. So clay is made up of colloids. So now we're looking at the smallest structural unit of a clay particle. Alright. The clay is almost microscopic for us. Alright? So we're looking at 1 unit in the composition of the clay. By the way, what is the charge of the clay particles? Like why water sticks to clay, for instance? Clay, yeah, it is negatively charged, naturally. The compounds that make up the clay, naturally, they give it a negative charge. And that's why you see the negative charge on the colloid illustrated there. And because it's negatively charged, positively charged ions can attach to it. You know, ionic bonding. It's a weak bond, but it develops. So now I can see on the colloid I have calcium, magnesium, aluminum, sodium. I have all these positively charged ions sticking to it. From all of those ions, if I look at calcium, magnesium, potassium, those are nutrients, those are bases. If I look at the sodium, aluminum, NaAl, those are non-nutrients, acids. Anyhow, and right here, I have the plant roots. You see the green structure, that's representing the plant roots. So the plant root doesn't extend all the way and touch the colloid to uptake the nutrient from it. So what happens, I have the soil water in between. Right here, I have soil water. And in the soil water, ions can dissolve. So now I call it soil solution. So what's happening here, you see this hydrogen ion on the plant root? It can be released to the soil solution. The soil solution will take it to the colloid. And then that hydrogen ion can knock off, can replace one of these nutrients, maybe calcium or magnesium. And then the magnesium or calcium or potassium, so it's gonna knock off a potassium ion. And when it gets available in the soil solution, it will go back through the soil solution to the plant root, and now the plant root is uptaking the nutrient and can use it to build its own, or to achieve its own metabolism. Okay? So that's the significance of the soil water in facilitating the transport of nutrients to the plants. Now, if you look how we're translating the visual illustration to the equation on the top. I have colloids, and those colloids, they have potassium ion associated with it. I have hydrogen in the soil solution, hydrogen aqueous, so it's in the soil solution. So the hydrogen will replace the potassium, and now potassium is in the soil solution, and through the soil solution, the plants are able to obtain. So is it clear what's happening there? Now, when we look at the colloid, and we look where the calcium, magnesium, calcium, potassium, they are setting, all right? These sites, we call it exchange sites, because it could be replaced. So I have the potassium got replaced, exchanged with hydrogen. So we call them exchange sites, all right? And the more exchange sites we have, the higher the possibility of having more nutrients attached to them. Right. Now, this will give me a soil chemical property, we call it cation exchange capacity, CEC. So what is cation exchange capacity? Oh, I don't, it's not. So what is cation exchange capacity? It's simply how many exchange sites I have on the colloid. The more exchange sites I have, the higher the cation exchange capacity. And then there's another chemical property that I can look at. It's called base saturation. So what is base saturation? I will go back to the exchange sites. You see these different exchange sites that we have? So if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Correct? From these exchange sites, the 10 of them, how many bases I have there? The actual nutrients. How many spots is occupied by an actual nutrient? 8. So the base saturation is 80%. It's 8 out of 10, correct? So I say base saturation is 80%. So this is another soil chemical property. So how do I figure out how many exchange sites we have? How do I figure out the base saturation percent? I have to follow a lengthy analytical protocol in my chemistry lab. So that's why we call them chemical properties of soil. Okay? So base saturation is the percent of bases that are existing as the exchange sites. High base saturation, it means high fertility. More nutrients. Low base saturation, low fertility. Because I don't have nutrients. I have exchange sites, but they are filled with non-nutrients. I want you to critique this sentence. High base saturation equal high fertility. Is this valid all the time? Let's assume I assess base saturation and I have a base saturation of 90%. Is it safe to make this a statement? I have high base saturation, so I have high fertility. What's missing there? So base saturation is the percent of the nutrients bases at the exchange sites. Why I need to be careful before making that conclusion? high base saturation equal high fertility. Yes? Well, I know the soil type. Yeah. I know water content. Just focus on the colloid there. Yes. I don't know how many exchange sites. If I have only one exchange site, only one, and I have a base saturation of 100%, because that exchange site is occupied by a nutrient, that's not really very helpful. If I have 100 exchange sites and I have a base saturation of 50%, it means I have 50 nutrients. So that's why I need to be careful when I say high base saturation equal high fertility. This is valid when we have a high number of exchange sites. But if I don't have exchange sites, it's usually, I cannot go with that conclusion anymore. And this is the last, right here, acidity. The last soil chemical property that we're highlighting as part of looking at the soil physical and chemical properties. So basically this is the pH of the soil. Guys, do you remember what is the most commonly measured soil property? Because of its significance and because of the ease of actually using it or assessing it, yes? Soil texture. Okay. I was correct maybe till I bringing up acidity or pH. This is another soil property that we tend to measure as much as texture, measure and report, or even more. Why? Super easy to measure. I grab a soil sample, I go to the lab, I have a pH meter, literally in 10 minutes, I know the soil pH. We don't have to grab the soil sample anymore. We have a probes, we take them with us to the field, we place it on the soil, I have the pH. I don't have the probe. I have a very tiny kit. It's called the soil pH kit. 2 minutes, I have the soil pH. Okay, great. So now I know the soil pH. By the way, what is the pH scale? You're familiar with the pH scale? Okay. What is the neutral value? 7, correct? And values above 7, what do we call it or what do we describe it? Okay. These are basic or alkaline. And below 7, acidic, correct? In the context of pH. Now, acidity or soil pH, what's nice about it, it correlates with cation exchange capacity or the number of exchange sites, remember? So acidity, which is affordable to measure, easy to measure, quick to measure, will give me an idea. It will not give me a numerical value, but positively correlates with the number of exchange sites. So instead of following a very detailed, lengthy protocol, and we need, by the way, for cation exchange capacity, we need some analytical equipment that are very expensive, correct? So that's another indicator for it. Now, ideally, we like our soil pH to be around the neutral value, 7. So 6.5 to 7.5 is the range we aim for most applications. We go to the field, I'm trying to figure out the nutrient availability, correct? I have no means, I have no resources, I figure out the pH. If it's off 7, I try to manage the soil to bring it close to that, to 7. Right? Because pH, it correlates with the nutrient availability. Close to a pH of 7, we will have for most plants, we will have the highest nutrient availability. So that's why we assess pH and we try to manage our pH to be close to neutral value of such. By this we will conclude looking at soil physical and chemical properties as part of this introductory class. Now I'll keep talking about soil, but I want to start looking at classifying soil. So this is what I'm aiming for. I want to get to soil classification. Remember that exercise? We go to the field, we excavate the soil depth 1 meter, 1 meter by 1 meter. Now when we do this activity, we're going to notice that we have different looking profiles. And then depending on the characteristics of the profile, I started classifying soil. Now the soil classification system that we will introduce in this class follows the Canadian system of soil classification. So all terminology and how I'm classifying the approach is based on our Canadian system. In the US, they have a slightly different system with significantly different terminology. And then under the FAO, which is an organization or a division within the UN, when they are looking globally at soil, they use also a different set of terminology to classify soil. So we're introducing our Canadian system of soil classification. Now, before we get to soil classification, I need to speak about soil profile, soil forming factors, soil forming processes. And I think in today's class we will only talk about what is a soil profile. This is a soil profile. You see this vertical exposed section of the soil? This is what we call a soil profile. Okay. When we go to the field and we excavate a 1 meter deep soil pit, and I'm looking at that soil, exposed soil, the vertical section that I exposed, this is a soil profile. Now when we do this activity, we will notice right away that actually any soil profile is made up of a set of distinct layers, horizontal distinct layers. Now when I say horizontal distinct layers, they're showing the properties that are different as I start looking from the top all the way to the base, to that 1 meter depth, or wherever I manage to get, 70 centimeter depth, 30 centimeter depth. Now the difference could be maybe in color, could be in structure, could be in texture, it could be anything that's obvious to me, anything that is differentiating a layer from the next one in the profile. Now these layers, we call them horizons. Within soil science, we refer to these distant horizontal layers as horizons. I think this is a better illustration of an exposed soil profile, and I'm looking at that soil profile from the top all the way to 1 meter depth, and you can see the distant horizontal layer. From the top, very dark brown, and then followed by a very thin gray color layer, and then followed by brown or red, and then switching to orange yellow, and then right here you see how pale, grayish, almost whitish color. So each horizontal layer with a distinct color for me is a different soil horizon. And the soil profile is made up of a set of horizons. So all of them together are making the soil profile. Now when I'm looking, you see the previous illustrations that we had? Okay, this is a schematic illustration. So it doesn't have to be that profile that I showed earlier. This is an example, a schematic illustration of a sample soil profile. So typically, on the very top of the soil profile, we will have the darkest layer in the profile. You see right here where it is literally black color? This is the very well decomposed organic matter. Remember the term humus? That's the letter H. It represents humus. And then up, L and up, it's also organic matter. So L for leaf litter, up for fibrous material, H for humus. So L and H, all of them together, LFH in the Canadian system of soil classification, this is representing the organic horizon. Alright, so if I go back to the previous slide, you see here on the forest floor, you see the leaves that are pointing to them. This is the L layer. L. And then can you notice right here, just below it, how I have material that looks like a mesh? This is the fabric layer, up. And then just below these two, I will find the very dark brown, well decomposed humus. That's the H. So all of them together, LFH together, they form the organic horizon. And this terminology, LFH, is only unique to the Canadian system of soil classification. In the US, they made it a bit simpler. They designate the letter O for organics. For us, it's a little bit more detailed. We're breaking it down. What are the components of that organic material? LFH. All right. So when I want to classify soil, I'm not concerned with the organic top horizon. The Canadian system of soil classification is mostly based on the mineral horizons. So usually, typically in the field, my first task is to scrape off. I remove the LFH. I don't want to deal with that. And I focus on the first mineral layer below the LFH. And then what is a mineral in my definition? Any layer that has less than 30% organic matter content, we consider it as a mineral layer. So when I'm talking about LFH, they're mostly organics. I can have a little bit of sand maybe mixed with them, or silt or clay, but mostly organics. If I have a layer that is mostly sand, silt, clay with some organics in it, I'm going to call it a mineral horizon, not an organic horizon. Now when we look at the mineral horizons, typically the top, from the top to the base, we just follow alphabets. So you can notice I have A, I have B, I have C. So the top mineral horizon right away, I will designate it with uppercase A. And then the one to follow with B, and then the one to follow with C. And below C, we don't have soil anymore, we have bedrock material. So once we get to C, anything below C we consider it, or it is actually bedrock material. That's the end of your soil profile. Now if I look at the top A, you notice how it's a little bit brownish in color? Why? From where this brown color is coming? Brown color indicates what? Organics. The top mineral horizon, which is A, right on the top of it we have H. We get some mixing happening. So I get some organics from the H mixed with the A. That's why it makes that mineral horizon brown. And that's why we are using the lowercase h. So this is a mineral horizon, A, that has organics in it. The lowercase h is for humus, organic. So this is AH horizon. So AH is the top mineral horizon that has some humus mixed with it. Now what about AE? You see, just below AH we have another horizon, we're naming it AE. The reason why I'm starting with A, because this horizon, it used to be part of the A, but over time, some processes altered its properties. Okay, so what is the process that's altered its properties? That section usually developed in areas with a lot of precipitation. Only. Water passing through a horizon will infiltrate iron oxides from the lower part of it. So water infiltrating through A will remove iron oxides. Iron oxides, they give the yellow-orange color, correct? When they are removed, it becomes pale in color. It becomes grayish in color. So when we notice that we have a part of A that became pale in color, we designate it as a separate horizon now, and we name it AE. More about horizon designation and how we're naming our horizons. I already exceeded my time for today. So more about this when we meet on Monday. Before you leave, feel free to pass me your answers if you provided them on a piece of paper.
Connection, yeah. One. Thank you. Elevator එක තියෙනවා මම ගත්තේ නැහැ. I see so මේ හරිය connection tunnels නේ. ඒවා නේ මොනවාද?
Probably not.
අයියෝ thank you elevator එකක් තියෙනවා. ඒක use කරේ නැහැ. ගෙදරදී යන්නේ නැහැ. අනේ තව එක ලක්ෂ එකක් තියෙනවා. ලයිව් ආවෙත් එහෙම වැඩ නිසාමත් නෙමෙයි ඉතින්. එන්න බැරි වුණා. ඒකත් අප්ඩේට් කරනවා නේද නැගි? තම ඔටෝ එන එක 18යි කියන්නේ. යා ඒක ෆික්ස් කරන්න.
Because we have the biggest plan.
මදාව ඉඳන්ගේ සමා වෙන්න ස්කෑම් වෙලා ඉන්නේ. Are we leaving the seat for Sophia? Okay. Put that in.
Are you flying? Okay, I was like, here, hold your phone.
Ada belah ni.
Did you see what happened downstairs?
What happened downstairs?
Oh, you didn't see it?
No.
It was like police. Someone was like yelling and saying stuff. I was like walking up the stairs and I just see police is like up this like near the stairs like oops. Did you on the assignment?
I finished up to 3. Like I have.
Oh, I thought you said you finished the whole thing.
No.
Is it bad?
No, the first ones were okay. I didn't look at 4 yet.
Dude, I didn't start it.
3 took a little while. Mendekat ini.
What week are we on?
I don't know. 12?
Oh wait, I think so. Graphs part.
Hey everyone. So next week is week of test 4, and practice for the test is already available. Check out all the questions in that practice test because the real test will have not only MCQ questions, multiple choice questions, but also short answers. In particular, you will be asked to give a BFS traversal on a given graph, and this traversal needs to be typed into a special place on Brightspace. number or label of every vertex, comma separated. So please take a look at the format, because the questions are marked automatically if there are some extra symbols, like even a space, then Brightspace will accept it as a wrong answer. Okay, so make sure that you read all the instructions in the practice test, so you know on the real test, be aware that if you list your vertices, for example, 3 and then 7 and then 8 and so on, you don't have any spaces here, and the list is only comma separated, and don't put any dot in the back. Okay, so just read the rules, and then everything goes well. This week is week of tutorial 6. Tutorial 6 is due on Saturday, so make sure you know about that. Assignment 4 is due this week as well. Okay, actual deadline is end of Friday, but you have extra 36 hours to polish it up. So Sunday noon, that's your late deadline. Do you have any questions about anything? We are coming to the end of the term, so. Okay. Yeah. This topic, we will discuss graphs today. This topic will be on the test. And I don't think I will finish today's lecture. There will be, another one on Friday. And that's the whole material that you need for the test. On Friday, we will also start proof by induction, and that topic is not on the test. But today's topic is, and I will not finish all of it today, so part of Friday's lecture is also on the test. Okay, so I will start with BFS and DFS. We saw animations, visualizations of both algorithms last time, but we didn't talk about code, about running time, about other features, and today we will do that. And I wanted to start with BFS, algorithm that is more complicated compared to DFS, but its code looks much simpler compared to DFS. DFS is a recursive algorithm. This one is not. Just to remind you how BFS works, it starts with whatever vertex you give it as an input as a starting vertex, and then it explores every neighbor of this one, and then it explores neighbor of this vertex, and so on. It moves in waves. How does this work? So here's my pseudocode for BFS. Input is graph and starting vertex. Algorithm will maintain two, let's call them data structures for now. One is known as T, that's a tree of my traversal. Vertices, and the first one, the starting vertex, goes onto the tree. And then we will be adding vertices and edges to this data structure to show tree of our traversal. It also has a queue. It maintains 5 for queue, first in, so first in, first out. It's regular queue for cache register. So my vertices are joining this, they will join the queue from the back. And from the front, I will be removing vertices to process, to look at their neighborhood. So the first vertex that goes into the queue is your starting vertex. And then we will add all its neighbors to the back of this queue. And if I have multiple neighbors, I will add them to the queue in order of their label, from smallest label to largest label. There is always, think about it as a sorted order of neighbors that they go into the queue in sorted order by neighborhood. Then I have a while loop inside. And while loop will be taking vertices from the queue. It removes vertices from the front of this queue, and it will observe all the neighbors. Here's a for loop that looks at all the neighbors of that vertex that was pulled from the queue. And if those neighbors are unvisited, we didn't see them before, we add them to the queue here. If W is not on the queue and was never on the queue, never during the runtime of this algorithm, then we process it. We first of all add it to the back of our queue, we add it to the tree, and we do this for every neighbor of the vertex that we are currently exploring. You can say why I am checking whether W, okay, just a second. Let's start again. Here's my while loop that takes vertices from the queue. Inside of it, there is another loop, for loop, that looks at all the edges of vertex that was just removed from the queue in this for loop. Okay, so now I'm interested to know whether at least one of those neighbors was never visited before. So if vertex was not visited before, it means it's not in T and it's not in Q. But why do I check both of those things? From logic perspective, it would be enough for me just to see if it's not on the tree. However, Q is a data structure that is much smaller compared to a tree, because for my tree, I only add vertices, and it's getting bigger and bigger and bigger. My Q, however, tends to be small data structure because vertices are removed from it. So in terms of logic, I could simply just check the tree itself, but I will be searching in a data structure that is a little bit bigger than Q itself. And to make my algorithm a little bit more efficient, I would like first to look at the Q because it's a small thing. And if my vertex is there, I don't need to repeat my search in the tree. Okay, so depending on size of your graph, depending on number of connections and on average how big is your queue, you can decide whether you want to go with queue and tree to do checkup or only tree. Okay. If we're interested in analyzing running time of this algorithm, I can see that I have while loop and I have nested for loop. For the while loop works with the queue. It removes vertices from the queue. So how often do you think we remove vertices from the queue? Throughout the runtime of the whole algorithm, what is the number of while loop iterations? Yep. N, right? So for simplicity, I will say N is size of V, number of vertices. And why I know it's N at maximum? Well, because here is even a remark here. We do add vertices to my queue, but if vertex was removed from queue, it will never be added again, right? Because we also check the tree. So if we only look at the queue, it is possible that the vertex I'm now considering for an addition, for additional traversal, it is possible that it was processed before, got deleted from the queue, but guess what? It is still on the tree. Vertex that was processed before never goes onto queue ever again. Okay, even if it's not on the queue at this moment, it is possible that it was on the queue, got removed, and we can find it in the tree. So this is a maximum number of while loop iterations. And why do I say, sorry, let me rephrase my question. What happens if my graph is disconnected? what happens to say I have one connected component and my starting vertex for BFS is in this connected component. And I have another part of the graph that is disconnected from this one. What happens to vertices here? Will they ever be added to the queue? No, right, because there is no way for me to go from this connected component to this connected component. I am only walking by taking edges. So you can use this algorithm, for example, to check if your graph is connected. Okay, we will talk in a second about this. Okay, so while loop iterates that many times, it's maximum possible, but get this smaller, because if my graph is disconnected, obviously I have no way to access the other connected component. Okay, now how about this for loop? How many times does this for loop iterate per each while loop iteration? Now let us look at the for loop. Well, yeah. Right, it's number of edges, but say yeah.
Like n minus 1, it's every possible connection on that vertex.
Maximally, yeah, you can say that. It's n minus 1. However, look, if I have this vertex, its degree is 3. So, for example, for this vertex, there will be 3 iterations of for loop. For this one, 2 iterations. For this one, no iterations. There are no neighbors. So the number of iterations, it's different, but we can express it in terms of degree of this vertex. So for one vertex, it's degree of that vertex. For another, is degree of that vertex. And what do we know about total sum of all the degrees in our graph? Yeah? It's 2 times e. So for loop, we cannot specifically say how much it iterates for this vertex, or this, or this, or that, but we can say combined, for the big picture, combined, for all vertices in my graph, it's 2 times e max. Okay? And again, why it's max? Well, because there can be disconnected components that I never visit, and edges are not processed from that part. Okay, so this gives us runtime for BFS, where my while loop iterates that many times, and this is a total runtime of this for loop, including all the while loop iterations. Okay, let's take a look at the animation. We saw it last time, but I just want to go through it again after you saw the algorithm. My starting vertex in this case is 7. So BFS algorithm gets graph and gets that vertex 7, and we start from here. 7 is on the queue. So when I come to my queue, I remove 7 from it. I remove 7, and I start processing neighbors of 7, which is 0, 6, and 8. And I do process them in order of their labels from smallest to largest. So I will not start with 8, I will not start with 6. I will start with 0, because it's the smallest label, goes to the queue, edge goes to the tree. Both vertices now on the tree, and this is edge in that tree. Tree of my traversal. Then 6 is added together with this edge, then 8 is added, and I'm building in purple edges of my traversal tree. Okay, we now processed all the neighbors of my 7. And there is 3 new vertices here, which is 0, and 6, and 8. What do I do next? Well, I come to my queue and remove front, whatever is sitting at the front of my queue. That's 0. And it has 4 neighbors, which is 1, and 9, and 8, and 7. And we process them from smallest to largest. So 1 is something new, goes to the queue. Then the next smallest is 7, but it is already part of my tree, so I don't even go there. Then I look at 8, and this edge doesn't give me anything new. 8 is on the queue. And then I see 9, that's a new vertex, so I add it to my queue together with this edge through which that vertex got discovered. Okay, and we continue. We go take 6 from the queue. What are its neighbors? Well, there are 5 neighbors. We process them from smallest to largest. First one, already explored, we do nothing. Second, vertex is something new, goes onto queue and into the tree. Then I have 7, nothing to do here. I have 8, nothing to do here, but I do acknowledge that this edge was, traversed in a sense, but it doesn't become edge of my traversal tree. I simply, I look at it and then I just discard it. And then 10, that's something new, added both to queue and to the tree. And we continue, so next vertex to be deleted is 8. From 8, I have nothing new, but I do look at this edge anyways. And so on. 1 doesn't give me anything new. 9 has something new here. That's 5, goes onto queue. This edge is, it's processed, but we have nothing new to add. Then we go take 2 from the queue. There are a couple of new neighbors that we never seen before. It's 3 and 4. So we add those. 5 was discovered, nothing new. 10 is known, nothing new. And we continue. There is only one unexplored vertex left, and we will process it after this edge is being processed, because 4 has smaller labels than 11. And then we add 11 to the queue, and we are done. So then 5 doesn't give us nothing new. 3, nothing new. 4, and then 11. So this is the queue. If we look at the history of queue, it gives us a traversal. And on test 4, this is traversals that you need to give to Bryce with question that asks you, okay, what's a traversal on your BFS tree? And for some reason, a very common mistake is to exclude the starting vertex from the traversal. I have no idea why, but it's been a very common error for years now. So please know that starting vertex is part of the traversal. It's the first one that's sitting there. Okay, so on test 4, notice, don't add any spaces between numbers, commas. It's only just numbers separated by a comma, and that's will be auto-graded. Okay, so let me show you the waves. If we align vertices according to the level of neighborhoodness with 7, so first wave of neighbors, second wave of neighbors, then we can see that we have a very short tree, and BFS indeed builds shortest path tree from 7 starting vertex to every vertex in my graph. Okay, if I bring all the edges back, all my original edges of my graph back, I can see a very interesting property, is that every edge either connects vertices within the same wave. For example, 1 and 9 connects vertices within the same wave of exploration, or it maximally spans 2 consecutive waves, like 2 and 5. There is never an edge, for example, that goes from 6 to 11. And why there is no edge that goes and maybe jumps over a wave? Why we don't see this connection in our graph? Well, think about it. If this edge, 6 to 11, was originally in my graph, 11 would be yellow. It would be explored during second wave of exploration, right? So we know that no edge exists like this. Okay, here's another question. If you're asked, here's a graph, can you tell me whether this graph has a cycle? You just reply true or false. True, yes, there is a cycle, no, otherwise. How can you modify BFS to answer this question? Yep.
Maybe instead of looking for ones that aren't explored, you look for vertices that have been explored?
It's easier. It's even easier. Notice my purple edges. Purple edges are edges of a tree. We know that trees are acyclic. So what are you looking for to just say, oh, there is a cycle? Look, if your graph contains at least one edge that connects vertices in your traversal that is not part of the tree, that edge closes a cycle. Right? Take a look at any edge. Take a look at any black edge here. It does close some cycle. Okay? So you, why I'm saying just to look at this connected component, because if your graph is disconnected and there are some edges there, let me rephrase it. For example, if you just look at number of edges, it is not representative whether there is a cycle or not, because maybe you didn't explore the rest of the graph, right? And you are dragging edges from that part. Take the component where connected component of your graph where BFS worked and explored it all, and if there is an edge in that connected component that is not part of your tree, traversal tree, then that edge obviously closes some cycle. Okay, let's take it. Let's take a problem that is a little bit more complicated. What if I ask you, do you have cycle of even lengths or cycle of odd lengths? How can you answer this question now? What is the observation? Yep. How would you find odd cycle? Okay, take a look at the tree. If my edge of that is not part of the tree, if an edge that is not part of the tree connects vertices within the same wave, then what happens? So here's, I have two vertices within the same wave. They are connected by an edge of my graph. And if they are in the same exact way, that there is a path, we can trace backwards, and maybe a starting point is somewhere here. We know that this length and this one is the same. Let's call it maybe as length x. So I have 2x plus 1, this one. So if you're interested in odd length cycle, you're looking for an edge within the same wave. If you're looking for an even cycle, like say there is a vertex from a different wave, and something like this happens, this is edge not from my tree, then you have an even length cycle. Okay? So again, if your edge is within the same wave, it's an odd cycle. If it spans between consecutive waves, it closes a cycle of even lengths. Okay? Because this is x plus 1 plus 1. Right? It's 2 times x plus 1. Even number. Okay, so now we see we using just BFS, we can check whether graph is connected or disconnected. We can find cycles or even answer whether the cycle has odd lengths or even lengths. Okay, so those algorithms can be modified to answer and solve more problems that we wanted from them. And this, by the way, also finds all the shortest paths from the starting vertex. Okay, so quite useful algorithm. Okay. Sorry, do you have any questions about BFS, breadth first search? Okay, let's talk about DFS. DFS algorithm seems a little bit more complicated due to recursion, but let us discuss what happens here. So here's the main part. DFS gets G, the graph, as an input, starting vertex, part of this input. It starts with a for loop that goes through all vertices and marks them as unvisited. So imagine every vertex has a flag that's a Boolean variable that can be true or false. True means it is visited, false means unvisited. So everything is marked as unvisited with false flags. I will have tree of exploration as before. It can be some data structure, and in your consecutive courses you will know that you can do it using maybe a binary search tree. Then you can add and remove things to this tree in log and time. Okay, so or you can keep your vertices in an array. Then some operations become less efficient, but other operations become super fast efficient, like adding new things in all of one operation and so on. So there are other things that you can think about later on, but for now we are in logic, and all we're interested is we have a tree of traversal. How you implement it, it depends on your problem, your graph, and there are beautiful tools to help you with that. Now I have explore function. That's a recursive function. It gets starting vertex as an input, my tree and my graph. And also notice I am given references to the tree and to the graph. Depending again on your programming language, you might not know, but for some programming languages, if you do something like this, those go as a copy of graph and tree. That's not what we want, because first of all, I will be copying then my graph over and over again. That's a terrible waste of space. And then my tree, as a copy gets populated, and as soon as that function is dead, the tree is dead as well. So we are not really growing anything. So be mindful about those things when you implement your algorithm using some programming language. I assume I'm giving pointers to those structures or references, not the copy of the thing. Okay, what happens in explore function? That's a recursive algorithm. So the first thing it does, it takes the starting vertex and marks it as visited, flips its flag to true. Then there is a for loop. We'll look at all the neighbors of my vertex V, of the starting vertex. And if the neighbor is unvisited, if we find unvisited vertex, we explore it, right? We add it first to the tree together with the H, and we explore it. And let me maybe run animation first before we talk about runtime, so I can show you how recursion works. Let's jump over this stuff. And assume here I am starting with 6. So I have explore call on vertex 6. And there is also a reference to the graph, reference to the tree. I will not be mentioning this right now. Okay, in my for loop, I look at here. Sorry. In my for loop here, I'm interested in all the neighbors of my vertex 6. And I will start with the one smallest label, which is 1. Okay, so I have a recursive call now to E with index 1. Right, let's take just a second here. I can freeze maybe one screen with a code. Okay, anyway, try to try to keep this code in your mind while I'll run animation. So here, for loop looks at all the neighbors of my vertex V, and it adds them to the tree if we have never seen them before, those vertices. And if that's the case, we call explore. That's a recursive call on this newly discovered vertex. In my case, it's 1. Okay. 1. Now, inside this function, there is for loop that explores neighbors of 1. And my smallest label neighbor is 0, so I have a recursive call to explore 0. And now I'm in this function with its for loop that looks at neighbors of 0. And all those calls are sitting in my stack together with all connected information. So again, do not copy graph, because graph will be copied over and over again. I do use references. Okay, I don't write it there to simplify, but graph reference to tree is given every time. From 0, I go to 7, my smallest neighbor. Explore 7. Next, I go my neighbor 0, smallest label, got explored, I don't take it. 6, explored, I don't take it. 8 is something new, I do take it, and I call explore on 8. From 8, I have lots of neighbors, but all of them we already know. So it looks like I'm stuck at 8, but what it really means is my for loop terminates, looked at all the edges, and then there is nothing new from 8. I terminate this call, and where do I go back? I go to the function that called this one. So we come back to functions that called this one. And I'm back to the for loop for 7. Keep exploring, I will keep exploring neighbors of 7. There is nothing new from 7, so this function also terminates. We delete it from our stack, and we go back to the functions that called it, which is explore on 0. One edge that is was not explored yet brings me to 9, and I say here's a recursive call to 9, and we keep going. From 9 I can go to 5, smallest label. From 5 I will go to 2. From 2 I will go to 3. Okay, so 9, then we go to 5, then we go to 2. And so on and so on and so on. So now, when I reach very end of my exploration, and I go back from 11, I go back to 10, I go back to 4, I go back to 3, I go back to 2, right? This is from 3, right? I go back to 2, then I go back to 5, then I go back to 9 and 0 and 1 and 6, right? I go all the way back like that, and I finally back to the functions that called me, which is, let me jump. I go and I appear here, and this function is now done. I simply output my traversal tree. So you can imagine if your graph is big, a lot of stuff can be stored on your stack. That's where a Stack Overflow can happen. So instead of using built-in stack like Python has, and takes care of this for you, you can have your own stack, your own data structures that you have full control over. You can create one in your code, and then because you have control over it, you will grow it as it gets bigger. You can shrink it when too much space is wasted. But this is a topic for a different course. Okay, so you be mindful that recursive functions do occupy a lot of stack space. Any questions so far? Okay, let's talk about runtime. If you look at this part, I see that this for loop executes v times, or we can call it n times. how do I analyze runtime of a recursive function? Well, it is hard. I cannot simply count basic operations here because when it comes to this one, how do I count, right? So we need to be a little bit smarter. We need to take a step back and see, in total, what happens here. And I know that each explore function has a for loop that runs degree of this vertex, right? So we can say for one vertex it iterates, say, 3 times because degree of this vertex is 3. For another vertex it maybe iterates 10 times because that's degree of that vertex. So then combined is just sum of those degrees. So that's where this comes from. That's this whole thing is a runtime of all explorer functions all together. Okay, I have degree of my vertex, and why do I have +1? Because if my vertex has no edges, like, okay, I remove that. So it is possible that you have a vertex that has no other neighbors to explore from it. We still do some of one amount of work just to, we arrived at that vertex, right? Okay. So we can also conclude that runtime then is similar to BFS. It's V plus E. And guess what? Can I use this algorithm to check if my graph is connected? I can, right? I can run DFS, and when it's done, I can simply look whether all my vertices were visited, if there is something unvisited left. So for example, here, after explore is done, before I output 3, I can put some little piece of code that says, do I still have unvisited vertices? If this is the case, my graph was disconnected. Okay? Because we mark all the vertices as unvisited, and if there is something unvisited still after explore function, that means we have a disconnected graph. Can we use this code to find cycles? Right, we can. Every edge that I discovered during my walk in the tree, every edge that is not part of my traversal tree closes a cycle. Right, so we do have beautiful tools like BFS and DFS that can solve other problems. Okay? You can modify them and they can help you solve different types of problems. DFS doesn't build shortest path from the starting vertex. It's a different technique, but maybe that's what you wanted. Okay. Do you have any questions? Yep.
In this case, the graph, how will that represent the data structure?
Oh, yeah, we will talk about this. You're right. We talked about given graph to both algorithms, but we never said how it looks like in a computer memory. For example, with a naive approach, you can say, you know what? Graph is just a set of vertices and a set of edges. Let's just give them as, I don't know, as a list. I can give an array of vertices, say 1, 3, and those are my vertices. And then I can give set of edges as a 2-dimensional array. Or I can just simply give it as pairs. Like 1 and 7 are connected. And if I'm talking about undirected graph, I will do something like this. It will be hard to work with such thing because imagine I arrive at vertex 4 and I need to know all my neighbors of vertex 4. I will have to traverse the whole set of edges to just find that neighborhood. And this can have quadratic in number of vertices. So that's not a good idea. Another thing, sorry. Oh, my bad, I did something in my presentation. Okay, yes, this place. Okay, another Yeah, I still have my. Okay, here I am. Another way, say, if I have a graph like this, maybe it's worth to represent it as a pointer-based data structure in my memory. That would be a very natural thing to do. So for example, for vertex 1, I have a memory location with some information and pointer that goes to vertex 2 in my memory. And then from vertex 3, I can go here. But then there is a question, how do I say get to vertex 3? How do I find it? So pointer-based approach is not efficient, and it doesn't really help us at all with solving, going from here to there. I'm still uncertain how I find, neighborhoods, how I find if there is an edge between 4 and 7. It's probably, we can say, okay, we can have the vertex together with an array of all the pointers to other neighbors and so on. It becomes very complicated system, hard to add new edges, hard to navigate. So instead, we have two beautiful techniques. One is known as adjacency matrix and adjacency list. So let us look at both of those to see what are their advantages and disadvantages. Let's start with matrix. It's quite simple to understand. So here's my graph, and here's how my graph looks like in computer memory, how I give my graph to the computer to deal with. This matrix has that many rows and that many columns. So row for every vertex and column for every vertex. Inside, I see it's is filled with zeros and ones. One says I have an edge. And I see that there is an edge between D and E. Here's the edge between E and D. And because my graph is undirected, I also see the same edge repeated here again from E to D. Right? The same edge between two vertices appears in my matrix twice. For example, A to D, there is an edge, but also D to A, the same exact edge. So I do store every edge twice here. What else you can see is that I do store many things that are not even edges. There is no edge from G to A, to B, to C, to D. They do not exist, but I still have some space for them. So my matrix representation is a bit wasteful on space, especially if your graph is sparse on edges, not many edges. But advantages is if I want to check whether there is an edge between vertex I and vertex J, I just ask, in all of one time, I have a reply, because I can store matrix as a two-dimensional array in my memory, and access to an array memory location is all of one, it's immediate. Okay? So to store a graph as a matrix allows me to check for any edge in constant time. Okay, that's a huge advantage. Disadvantage here is that if I'm asking what are the neighbors of G, like BFS has vertex G and it says I need to run for loop on neighbors of G. Here I say we will have to walk through this row and see what are its neighbors. So I come here. A is not a neighbor, B is not a neighbor, C is not a neighbor. And that takes time until I find finally neighbor of G. And what is the runtime of this operation in the worst case? How many steps do I spend to find neighbors of G? It's length of this row, right? It's O of n. It's a linear time to walk and find all the neighbors of G. Okay? So that's a disadvantage. But this system can adapt very well to non-simple graphs. For example, if I want to store multiple edges, how do I modify my system? say I want between BC, I want to have 3 edges between B and C. Right, we can simply, instead of 1 here between B and C, we can put 3 here. What if I want to introduce self-loops? Where do self-loops reside? Yeah?
Just on like AA, for example?
On the main diagonal, right?
Yes.
So if you see 1 on the main diagonal, this is the main diagonal, that tells us that there is a self-loop. For undirected graphs, my matrix is symmetrical along the main diagonal. So technically, I could save space and to store only half of my matrix. But then there is a problem of, okay, what if I want to add an edge? What if I want to remove something? I will. So we do keep the whole matrix. Okay. So here's definition of matrix. That's for undirected graph, we have symmetric matrix. For directed graphs, that's not the case. And for simplicity, I will call size of Vn and size of E m. Advantages of matrix is that very fast we can check whether there is an edge between 2 vertices. It can be done in all at one time. Disadvantages, well, it is hungry for space. You saw that we store every edge not only twice, but also we store edges that do not exist. Lots of zeros in that matrix. But if your graph is a complete graph, and it has lots and lots of edges, we call them dense graphs, then technically no space is wasted because your graph really has lots of edges. So that matrix is not populated with zeros, but mostly with edges. So that's a good thing. All neighbors, not easy to find. It takes linear time. Let's take a look at the directed graph. Say if I, let's take maybe G. Okay, so here, if I look at the row, I see there are 2 edges. To G itself, that's a self-loop, and also to H. From G to itself, and also to H. So every row represents outgoing edges, edges that leave G. So then, where do I keep edges that are incoming into G? Well, then you consider your column. My column tells me incoming edges. So there is an edge from A to G, right? Here, from A to G, incoming. Then there is one edge from F, here it is, incoming. And then guess what? Self-loop also incoming edge, right? It's both outgoing and incoming. Okay, so nice observation. Rows give you outgoing edges from that vertex, and columns give you incoming edges. Okay, any questions about matrix? It's a simple technique. Yeah?
How can you tell the matrix is directed or undirected?
If it's we usually don't do that. When graph comes in, we usually tell if it's undirected or directed graph. But if you see that it's not symmetrical along the diagonal, then it is for sure a directed graph. And also, if you see that it is directed but symmetrical along the diagonal, you can cancel all the directions because it now really just every connection is a two-way street. Okay. Another disadvantage of this system is what if you want to add a vertex? Well, then you have a problem because matrix doesn't really grow on its own. It's a two-dimensional array, and the best thing you can do is just to create matrix that is bigger than your original one, copy everything from old matrix to the new one, and then, add a new vertex there, because it comes with extra row, extra column. So sometimes it's a very expensive operation because size of our matrix is quadratic. It has n by n dimensions. So that size is big. Copying quadratic number of elements, that's time consuming. So we usually, when we do this, we create matrix that is not by one row and one column bigger. We may create a matrix that may be twice bigger than the original one. Okay, depending on whether you anticipate extra additions or not. So that's something to consider. Okay, another system is called adjacency list. It doesn't waste too much space. It only keeps what is needed. But some of those operations become slower. Let's take a look at the list. So here I have an array for every vertex in my graph. Size of this array is this size of that array. From each cell, there is a pointer or reference to edges that attach in that vertex. For example, 0 is connected to 1, 2, and 3. 0 is connected to 1, 2, and 3. Then I see that vertex 1 is connected to 0, 4, and 5. Vertex 1 is connected to 0, and then to 4, and to 5, and so on. 2 is connected to 0 and 4. 3 is connected also to 0 and 4. 4 is connected to 1, 2, 3, 5. 4 is connected to 1, 2, 3, and now 5. And 5 is connected to 1 and 4, and we're done. I still save every edge twice. How did this happen? For example, edge from 1 to 4 is stored here from 1 to 4, but it is also repeated again in this list. So we do store every edge twice, but we do not store edges that do not exist. Okay, we do not store zeros like matrix is. Matrix stores a lot of zeros. Here we don't store edges that do not exist, but we do store every edge twice. In undirected graph, if my graph is directed, I store every edge exactly once. Also, this system is very nice because now I have my neighborhood given to me right away. For example, BFS, DFS, they rely on this information, and here I have all the neighbors given to the algorithm immediately in all of one time. That's a very fast operation compared to matrix. But if I want to ask, if there is an edge between those two vertices, what I do, I access, in my array, I access location at index I, and then I will have to walk through its neighborhood list to see and find maybe J is part of it. So it's no longer O of 1, but what is that? What's the runtime of that? Right, it's O of degree of that vertex, how many neighbors that vertex has. Okay. Advantages, it uses this much space, which is exactly size of our graph. It doesn't store edges that do not exist. Neighbors are easy to find. All neighbors are easy to find. So BFS, DFS work faster with this system, especially if your graph is not super dense. Disadvantage is now to check whether those are connected by an edge from O of 1 and matrix becomes this running time. Okay. So here are two systems, and usually when you need to understand which one to use. You will have to answer two questions. You are solving some problem, right? So what are the operations you do in your problem, and that will be, it can sway a decision whether to use matrix or list. So if you need all neighbors like BFS and DFS, adjacency list is a little bit faster on it. If you often check whether there is an edge between I and J, you should probably go with matrix because it has O of 1 axis. So here's just a comparison of different operations. So you can discuss that. And the second question is, what is size of your graph? And for size, we look at the number of edges. So imagine this on this axis, I have number of my edges, and it can be from 0, like no edges at all the way to all possible edges, like in a complete graph, but maybe even more, like also self-loops and also multiple edges. It can go on and on and on. So let's start with sparse graphs. For example, if you have little number of edges, like this graph, or maybe your graph is a tree, which in reality, many graphs are very close to trees. If you are dealing with a tree, it has this -1 number of edges. So it's on the scale, it's sitting somewhere here. And those are known as sparse graphs, not many edges. If your graph is sparse, you go with the list. If your graph is dense, like a complete graph, you have that many edges. So you probably want to use matrix. Let me explain why. Another thing. So if you know that your graph maybe has some restriction on number of degrees, say you know that maximum degree in your graph is 5. But the size of your vertex set may be in thousands or millions or billions. But every degree of each vertex is no more than 5. It can be 1 or 2 or 3. Then you can go with a list, adjacency list. And why is that? Let's look at this table. Adding an edge is O of 1. Removing an edge, compared to matrix, is slower, but if my degree is not really big, I only make, in the worst case, if I want to delete some edge, I make 5 steps maximum to find edge that I need to remove. And that becomes O of 1, because 5 is a constant. I know that I will never make more than 5 jumps in my neighborhood list. So this running time, despite that it looks like scary, if my degrees are small, that's comparable to constant time in matrix. But advantages here is I'm not wasting space, but also operations that seemed like time consuming also becomes fast. Okay? So again, size is a big concern. And sparse graphs are usually, we usually store them as lists because everything here becomes very fast. Okay, there are some exceptions. So matrix is used obviously for dense graphs because if you look back, if your graph is dense and you try to store it as a list, it occupies, if this is quadratic, then your space is actually n to the power 2. So the same as matrix, but you lose on speed. To check if there is an edge between I and j becomes O of n. Okay? This becomes O of n in the list, but it's still O of 1 in matrix. List, in a list, this operation becomes very time consuming because lots of edges means big neighborhoods. A lot of walking to do. So if I'm dealing with a dense graph, matrix is my choice. Also, there are some interesting mathematical solutions that exist on matrices. For example, if you're interested to find all the shortest paths between all pairs of vertices, not just from starting vertex 7, but from all of them, you don't run BFS n times, right? You don't do this. There is an amazing algorithm that can do this for you in log n time, but it relies on matrix multiplication, so it's better that your graph stored as a matrix. Then you have super fast algorithm to answer questions of this type. Okay, and in all other cases we do use a list. Any questions about two systems? Okay, let's talk about another interesting property, and that's about bipartite graphs. Okay, so imagine I have this graph, and I want to split vertices of this graph into two sets, left set and right set. The split will pull all the edges apart. So I do want to make a partition such that every edge only exists in partition, connecting vertices from left to right set. I don't want any edge to exist between vertices in the same exact set. I only want my edges to exist between two sets, like here. Every edge is between sets. Or you can think about it this way. Every edge connects red vertex with a blue vertex. It never connects to red vertices, it never connects to blue vertices, right? It's only in between. So endpoints of this edge are different in color, in sets. And I want every vertex to participate in it, means left plus right union covers all my vertices, nothing is left behind. And also every vertex is either in the left or right, but not in both of those things. Okay? Two sets are disjoint. Okay, so I took this graph and created a partition. You can see that those labels of vertices correspond to this graph, and I can now say that this graph is bipartite. Here's another bipartite graph. I can take, so that's how it originally was drawn, but I can draw it this way, and this is known as K33, where I have three vertices on one side, three vertices on the other side, and this graph has all possible edges that do not break the partition. There is no edge that goes from blue vertex to blue vertex, no edge that goes from red to red. But all possible edges that exist in between, this graph is known as complete bipartite graph. So in general, if I have complete bipartite graph on m vertices in one set, n vertices in the other set, what's number of edges? What size of its edge set? For this here, for this one. Yeah.
Is it m times n?
Right, it's a product. It's m times n. Because on one side I have m vertices, and each of those is connected to every one on this side, right? So it's a product m by m. Okay, so let us talk about graphs that can be partitioned and graphs that cannot be partitioned. So here's a partition that clearly shows me that the graph is bipartite. But say, imagine I add edge between those two vertices. I broke the partition, but can it still possible to revive it to show that this graph is still bipartite with extra edge? Yeah. Right, just to move, just to change my partition. So I take blue vertex, move it to the left, I'll take red vertex, move it to the right. And now we can see that it is bipartite. But not always I can fix this thing. What is the smallest, simplest graph on 3 nodes that cannot be bipartite? What comes to mind? Yeah?
Having both a connection outward and inward.
How does your graph look like? 3 vertices only.
Or just three connected.
Like a triangle, right? Yeah, so notice, if I have something like this, I cannot make the partition. It's not possible, right? There is always an edge that connects vertices within the same set. So if you notice, there is a triangle in your graph. So it means you have a subgraph of your graph that is a cycle of size 3. This graph cannot be bipartite because there is no way for me to fix partition. Okay, let us now summarize. I know that graphs without cycles are for sure bipartite. Okay? So graphs without cycles are bipartite. I can run DFS to do the partition. So imagine, or you can run BFS or DFS, doesn't matter. We start with vertex, we mark it, say, blue. Then on next step, we mark vertex as red. Next step, we mark neighbors of this red vertex as blue vertices. Next step is the other color. So for example, in BFS, you have iterations, right, of your while loop. You can see if it's an odd iteration, you choose one color. If it's even iteration, you choose a different color. So you can run BFS on your graph and color it, and that will be partition. Okay, graphs that don't have cycles like trees, they also bipartite. So tree is a bipartite graph. But I want to say that having a cycle is not really a problem. Say if I have graph like this, it has its C4, I can still make a partition. 1, 2, 3, 4. I can make a partition. I can put vertex 1 and 3 to one side and 2 and 4 to the other. 1 is connected to 2 and 4. 2 is connected to 1 and 3. 4 is connected to 3. And we have our partition. So having a cycle is not always a problem. So what's the bottom line? Which cycles I don't like? Yep. Right, cycles with odd number of edges, like 3, 5, 7. Those cycles are not bipartite, but cycles of even lengths are fine. Let's do 𝓐𝓫ᴅᴜ, because I can forget about this. Just a second, I'll open. Okay, so there are a couple of questions for you to think about. So imagine I have a population, say, of 𝓐𝓫ᴅ, and I would like to build siblings graph. Means every person in 𝓐𝓫ᴅ has a vertex for them, and two vertices are connected by an edge if those two people are siblings. Which system you use, matrix or you use a list? This doesn't look good. I don't know what happened. This is an opposite of what we talked about. Think about size of this graph. There are lots of vertices, but what's about the edges? There are not too many. We don't have too many siblings. It's usually a small number. But you feel like it's like a bacteria situation that we just have millions of siblings. Okay, this is weird. So the graph is sparse. The graph is sparse. I would use list because it doesn't have too many edges. Okay, let's take a look at another question. How can you determine if a graph is bipartite? Okay, this is much better. Let's talk about difference between option 1 and option 3. So option 3 is the correct one. Option 4 says perform BFS or DFS and check if it has no cycles. Well, it will answer correctly to some of the graphs. But remember that having a cycle not always a problem. Graphs with even length cycles, they can be bipartite. So there is no problem with that. So despite that algorithm, for example, from option 1 can correctly answer some of the inputs, it will answer incorrectly inputs of this type. So it's part of maybe some bigger graph, and this was marked as not bipartite, but it actually is. Okay. Thank you for doing this. Let's just go back to. Okay, last time we talked about complete graphs, and we often observe them not as a graph on its own, but just a subgraph of some other graph. So, for example, K4 is a subgraph of this graph, and K4 looks like that. Also, this K4 is drawn using planar drawing, no crossings between edges. This is the same exact K4, but with some intersection here in between. So imagine now an interesting problem. I would like to color vertices of my graph, not into two colors as before, as to have a partition into two sets, but imagine I'm assigning a color to every vertex such that every edge connects vertices of different color. So here I have yellow vertex and connects me to red, to blue, to red again. I used only 3 colors here, and I was able to assign colors to each vertex. And there is no edge that connects vertices of the same color, no edge. So ideally, I would like to color my graph, to assign a color to every vertex, no uncolored vertices left, but I also want to minimize number of my colors. Because ultimately, I can have that many colors and give unique color to every vertex. My problem then is solved, right? But I used too many colors. My goal now is to minimize, to use as little number of colors as possible. So is it possible to bring number of colors here to 2? Now I'm using 3 here. Is it possible to bring it down to 2? Take a look at this graph. Can I use maybe red and blue only? Yep. Okay. No, we cannot. Yeah. Yeah, so what we notice when we try to do this, we notice that we have a triangle. That's case 3, right? We have a triangle here. This is also known as clique of size 3. And to color just this part, I will use 3 colors. Complete graph on n nodes will use n colors. Unfortunately, why? Because if this is red, none of those can be red. So I will say, okay, you will be blue. But then this one is connected to red and connected to blue, so it can be neither of those two things. So maybe I will say it's yellow. So if you are dealing with a complete subgraph, clique of size n, you will spend n colors on just coloring that part. You can reuse colors you use here for other parts of the graph, but you cannot go with less than n. You cannot go with less. So let us take a look at this example. What's the minimum number of colors known as chromatic number? What's your chromatic number here? What's the minimum number of colors to color this graph? And the trick is to look for the biggest clique. Yep? 5, right? 5 colors. How do I know? Here's K5. I have K5, and I will spend 5 colors just to color this area. And then I need to be very careful. Say if this is a red, none of its neighbors must be red. And so on. But 5 colors, that's minimum that I will use. Okay, another one. What's a chromatic color here? Chromatic number here? Yep. Yeah. It's 4. Yeah. Here is K4. Okay, this is K4. Notice that 8, 3, 5, 7 is also K4. Okay, 8, 3, 5, and 7 is, oh no, sorry, my bad. Cancel that. This is not K4. Okay, this edge doesn't, this edge connects 8 and 9 and then 9 and 5. This edge doesn't go through behind 9. Okay. So here are a couple of examples for you. We'll talk about coloring next time again, but for now I just want to show you a real-world problem, such as coloring a map. And to color a map such that two neighboring countries have different color becomes easy when we translate our problem into a graph representation. There is also a very interesting theorem. It says that any map, any real-world map, can be colored using 4 colors. Okay, any real-world map can be colored with as little as 4 colors only. Maybe later you will notice why not, like, what does it mean if your graph is 5 colors? It means that it cannot be planar. Graph that represents a map is always a planar graph. We will see next time that K5, for example, is not planar. Means it is not. It's never a map of some kind. Okay. Otherwise, I will see intersections between countries. Countries are not neighbors, but kind of overlap. Okay. Thank you. We will continue with this topic on Friday. See you on Friday.
Let me tell the vlog. Hey guys, so we just finished class. And so, bro, my hands are freezing. I think you gave it to me. Wait, you want to say hi to a vlog? Huh? Girl, why we're so opposite? Yeah, that's weird. Say hi to a vlog. Back down. What's that? Vlog. Oh, vlog. That's
If you're honest, you would know. You would be honest.
Thank you so much. What? Thank you. No. He's gonna find it first. He's gonna do a recommendation. Hi. No, he's supposed to go. I'll tell you what he said. Oh, look at you, girl.
I should. I play the
Are you still live?
I am still live.
It's so cold. I don't know why I'm so cold.
Do you want to say, oh, what did I do? You want to say hi? Hi. Nini. Bye. See you on Friday.
Oh god, it's getting really bad.
Bro, you can tell like the class is like slowly like declining.
I know.
Slowly like.
Yeah. God, they are so low.
Yes, I am. Oh, sing her. Yeah,
Plus this assignment, like on top of
Her name!
Yeah. Assignment, I'm like, no.
I And she's also Sri Lankan, so they know how to type it.
Sorry?
She's also Sri
I know,
Lankan.
and then I looked at it, I closed it. I was like, no, right now. Like everything I look at, I'm like, okay, I need to go back. Like, I can't remember anything.
Yes. Have you guys started the assignment?
No.
Yes. For once, I started early.
Yeah? That's good, that's good, that's good.
Exhausting. But you're like on question 3, that's so bad.
Yeah.
That's good, that's so halfway done. It's only 6 questions.
Oh yeah, that's
Thank
true.
God,
That's
bro.
true.
On the opening.
Bro, I literally just did the latex one. I literally just put it in class.
Pacha, mana ada?
Wait, I'm gonna ask, wait. Bye!
Oh, wait.
Wait, are you going to library?
Yeah.
Hey! Wait, did we?
You're not from math tutorial, right? 'Cause
No.
I'm skipping it. I have to stay for my midterm. Right?
I'm skipping too.
Okay, good. If you're skipping, I was skipping. Dude, for the math assignment, I look. I'm not gonna lie.
The discrete one.
Yeah, bro, I look. Because I'm not gonna start
I'm
it
looking
until-
at all the like practice stuff.
Is it actually hard?
So far, it's been okay.
Girl, you're
Question
so-
3 was.
Oh, thank you, girl. Do you think it's like
a lot.
I want to start on
She's not gonna go to the
Friday.
library.
Oh, okay.
Yeah.
I'm going home anyways.
You're leaving. Why are you leaving?
Yeah, she's gonna leave.
The trio is not gonna be trio, bro.
සිංහල කොල්ල කෙල්ල ඉන්න කොල්ල නැකි ඔව් ඒක තමයි.
Bro, you're always wrong. What are they saying?
No, I'll go from there.
Yeah.
Bye.
Why are you laughing? What?
Oh, but if I go from the tunnels, the line is gonna disconnect.
Oh, yeah.
That's fine,
It's fine. Okay, I'll come
No,
with you
it
guys.
disconnects bad. Like, it lagged at the most awkward face you ever made in history.
I know. Who was that to? I was looking down.
Wait, where are you gonna go?
I'll go from Minto.
Wait, that would have been good vlog content.
Get out of here.
Wait, no, I'll walk with you guys to the library and then.
Okay! That sounds good.
Okay. Principal Lanani University.
What's so funny? How am I an NBC beta? Just for inspiration stuff.
That's perfect. You know, oh my god, yeah, me too. I wonder how much more students I got for that. I just
මේකේ අමාරු නියම් පොඩි වාහන වගේ දෙයක්. ඒකට මම මේ art.
Wait, is it didn't cut?
No, it's working.
Oh, wait, that's so good. Guys, who do you think is taller? Like, genuinely? Like, genuinely? Look at this.
It's just your band.
Hashtag hater.
All people?
No, it's been saying 12 the whole time. I think it's frozen.
You're getting your steps in today, bro. You're gonna walk all the way there.
Are we taking them? Hell no. Okay.
Bro, genuinely, when I first got to uni, I did not know about the shortcut. Like the elevator shortcut, right? And then people were like, bro, I take the elevator. I'm like, where? Are we in the same uni, bro?
Yeah.
But then, it's been so long since I took the ramp.
Same.
Thank God, bro. This ramp, bro? Yeah, obviously not.
I think it lagged a bit. Okay, I'll do this.
Oh yeah, I remember. That was so coincidental, right?
Oh, and we have one more though.
This is nice though. I can usually turn the camera.
Yes.
Yeah, this is gonna be so long. We literally could have skipped the stairs. I was just being lazy. I didn't want to. No fast. Oh my goodness.
Vika. Elevator tinggi. Thanks hari ni.
Wait, are you coming to the library with us?
Yeah.
Oh.
I'll come in and leave.
Oh, you might as well stay.
Sri Lankan ko di tiro min. Meeting. No.
Oh, you're ready?
Yeah.
Actually, it's necessary. It's triple big bang.
Oh.
We're the big bad gangs. It's a good thing. Wait. Want to say hi? Oh, okay. Hi.
Whoa.
Cheap. Yeah, just go to Egypt. Egypt is cheap. Yeah, bro, $1.
Cut your weather.
I can sense it. My peripheral vision, I can sense it. No, bro, I don't even Oh, here. I don't like to be again.
Hello.
Oh, do you guys have anything today or no?
No, I'm leaving.
Discrete. I've been walking on the screen. But it's okay. Just comes and yeah. So much. Oh my gosh. Much to discuss. Yes. Where are you guys gonna sit? She's gonna go.
Yeah.
But me and Melissa, go after the house at 2:30. But my prof was sick on Monday, so I don't know if he's gonna come today. Yeah. But Loki, like, he comes or does not come. It's literally like he's gonna post them. I don't know. We'll see.
When your algebra test on Monday, I bombed it. I didn't study.
Wait, you had it on this Monday?
Yeah.
Wait, I thought it's next week. Most people have it next week. I have it next week.
How was it? It's because I didn't study, so I didn't know what to do.
So you had the CS and the Lennon.
But think about it, like, yeah, you're gonna take the best out of my 3 tests.
For Lennon?
Yeah, it's 15%, and I did good on one of them. But then my final was 80%.
Oh my god.
Yeah.
Oh, because you did bad on the other
Yeah, I did bad on the other 2. Like, genuinely bad.
Oh my gosh.
I gotta lock in for the final.
Oh, it's same. 80%. That's worse than coxsci.
Yeah.
It's like 70%. Okay, but it's linear algebra. It's like, just do it. Yeah,
Got
do
this. හිටගෙන මොනවද කියන්නේ කට්ටිය කතා කරන. Young ගෙදර කට්ටියට බයි.
Oh my god, I've been reading. No, I've been reading. 2 weeks ago, last week or something. Oh, it's an update for both. Like, when you're gonna come back. So now we're both surprised. She said come down. Where down? Is she lost? She's not the camera back. Okay. Where are you sitting? Oh, wow. If you're lucky, I might need a bigger table. I'll go hunting for a table. Okay, I'll be back quickly. Yep.
I'll
See you.
go too. Bye.
Okay, bye. Bye, guys.
Tell Melissa I love. Bye. Nah, they're not in the camera. Up stairs ගමු. නැත්තම් connection යන්නේ. ගෙදර. ඔව් lecture ඉවරයි. library එකට ආවේ.
Okay.
Look how subtle the shade though.
Yeah.
Who's Chris?
The other girl.
We got first meetings.
එදින යන්න දෙන්න. අද සීතලයි දන්නේ නැහැ. Tunnels signal නැහැ එකයි. හරි නේද? එදින යන්නේ අද. Oh, ගෙදර යන්නේ. Cerama සීතලක් නෑ නේද? Yes, train එකට යන්නේ. දවසක tour එකක් දෙන්න ඕනේ නේද? මම campus එකේ buildings ටිකට ගිහින්. කවුරු හරි ඇඳලා. ඉස්සරහ එනවා පාට කොඩියක්. අම්මා එන්නේ කෝච්චියෙන් බැස්සම. Yummy. Pagane, edigan. තනියම යන්න පුළුවන් බස් එකේ. එතකොට පැයක් වගේ යනවා ගෙදර යන්න. ඉතින් අම්මා එනවා. විනාඩි 8යි යන්නේ ගෙදරින් නම් ට්‍රේන් ස්ටේෂන් එකට. කාර් එකේ. ගෙවල් පැත්තෙත් මේ වගේ තමයි. අර එදා දිවේදා තිබ්බේ.
There were, but
අර ගෙදර ළඟ ට්‍රක් එක ඒක නෑ ඒක දැන් දවස් ගානකින් තිබ්බේ නෑ. කියන්න අයිස්ක්‍රීම් වලට හිම දැම්මේ නෑනේ. අන්න Canadian geese. අනේ ඒ දුවන්නේ. කාර් තියනවා ලයිසන්ස් නැත්තේ තනියම යන්න. අනික මේ කැම්පස් එකේ පාකින් ගන්න. අයියෝ කෝච්චි තාම ඇවිත් නෑ. ඒ දුවන්නේ මං. මම මෙහි ඉපදුනේ නේද වෙලවල කරලා නෑ. මේ තියන්නේ උදේ හිටපු බිල්ඩින් එක. අලින් පස්සේ තියන්නේ. කෝච්චිය තව විනාඩි 7ක් යනවා. දෙකද? Oh, මේ මොකදනේ? ඇතුළට යන් මට සීතලයි. ප්‍රශ්න නැහැ. මේකත් warm නෑ. ඒ ඉතින් හුලං ගන්න. heating තියෙනවා. අර කෙබුවත්. එතෙන් තියෙන පොඩි බටන් එක. දියන්න බෑ. අද එහෙම අර දියන්න පුළුවන් විදියට නෑ.
Ja, شوفي مروان ونشوف.
ලියන්න ඉතින් කොහොමද ලියන්නේ? ලියන්න බෑ. ඒකන් ජනේලෙ තියෙන. අනේ ෆ්‍රස්ට් වගේ හැදෙන්නේ. නෑ මේ ට්‍රෙන්ඩ් එකේ වේගෙන් යන්නේ. අයියෝ ඉතින් මෙතන ඉන්නකොටේ. දියවැඩන්නේ මෙතන ටික ආවද? අන්න ප්‍රොටෙස්ට් එක. මොකද? මෙහෙම මේ මොනවාද? මේ ස්ටුඩන්ට් ලෝන් එහෙම දෙනවනේ ඉගෙන ගත්තේ. ඒව අඩු කරලා ඒ දෙන ගාන. ඒකට තමයි ප්‍රොටෙස්ට් කරනවා. මං එදා ලිව්වානේ කට්ටියගෙන මගේ ඇඟිල්ල ගැලිවිලා වැටෙනවා තා ටික වෙලාවේදී හිටියනවා. Good. Bessie. මට ෆස්ට් ඉයර් එකටම කීයක් කියද? පළවෙනි සෙමෙස්ටර් එකට 7000 ගණක් ගියා මම හිතන්නේ. Yeah. $. ඒ වගේ යනවා. ඒ ෆස්ට් ඉයර් එකට ඉතින් අවුරුදු 4ක් නෙවෙයි මම මතක නැහැ කලින් ගණන් ටික හැදුවා මට දැන් මතක නැහැ.
Attention. The line 2 train southbound to Lineback is arriving.
නංගි වියා ගිහින් යන්නකෝ.
Attention. Le train de la ligne 2 en direction sud vers Lineback entre dans la station. Veuillez vous éloigner du bord du quai.
දැන් කවුරු හරි අම්මට මැසේජ් එකක් දානවා නැත්නම් විනාඩි 6කින් කෝච්චියෙන් බහිනවා කියලා බං. පුටු තියෙනවා. ට්‍රේන් එකේ සිග්නල් නැති වෙන තැන් කීපයක් තියෙනවා. අන්තිම හරිය එහෙම නැති වෙනවා.
Positioning.
Southbound to Lens, direction sud,
Hello, me.
next station, Munsell. Prochaine station, Munsell.
Padain. එපා වෙන්නේ නැත්තේ කියන්නේ මම හැමදාම කරන්නේ නැහැ නේ. ඉතින් ඒක නිකන් ගැටියක් තියෙනවා. කවුරුත් මෙහෙම කරන්නේ නැහැ ගොඩක් අය. සීයා මන් දන්නේ.
Please do channel my Sakrapara.
Super nice. එයාලවත් ගෙනියනවා ට්‍රේන් එකේ. විශාල කරදරයක්. සාන්දියා මාව හෙන්නද? අයියෝ දැන් හරියද? හරිද? Okay. මේ ට්‍රේන් එකේ හෙලෝ ගලේ අයියේ. ඔයාට තමුණනේ membership. සිංහල පොඩි කාලේ නම් අම්මා ඉගෙනනවා. ගෙදරදී සිංහලෙන්ම කතා කරන්න කියලා තිබ්බා. රට කැනඩාවේ. channel my sakrapara saskapara sukurpa sacrifice Nandi ඊළඟ මාසේ බලමු වැටෙයිද කියලා. නංගි විශාල කරදරයක් වන් වෙද්දී අන්තකට හරි. වෙලාව දැන් 1:33.
විශාල කරදරයක් වුණා නේ මේක.
ඔය ස්ටිකර්ස් එහෙම දාන්න පුළුවන්. මොනවාද emojis? Please to channel my sakrapara saskapara sukurpa sacrifice Ayun yan na ito. Kaya lang ito yun. Ito na yung taray. Canada rin eh. Ada polo rin. Tama ka na.
Southbound to Lineback. Direction sud. Lineback.
Not be stuck.
Next station, Greenboro. Prochaine station, Greenboro.
ඒක තමයි කැමරාව එහා පැත්තට කරේ. නෑ නංගි. සල්ලි මගේ කසින් නංගි. මගේ නංගි very old. Oh, එයා තමයි නංගි. Oh, නංගි කැනඩාවේ ඉඳලා. Momenti. විනාඩි 17යි. මේ train stations කියන අම්ම නෙමෙයිද කොහෙද මල්ලිද මල්ලා.
South Key Station. Connection to Line 4, Airport. Station South Key, correspondant vers la ligne 4, Aéroport.
හරි. තාම වඩින්නේ නෑ. නෑ මේ සතියේ දෙන්නට නිවාඩු මාර්ච් බ්‍රේක් එක. මට හිතුණා. මොකද වෙන්නේ අබරංගෝ අයියා. ඔව් මන් තමයි වැඩිම. අයියෝ අම්මා නෙමෙයි ඔය අනිවාර්යෙන් ඉන්නේ මල්ලි.
Southbound to London. Direction Sud. Line back.
Hello, හොඳින් ඉන්නවා. ඔයාට කොහොමද?
Next station, Legion. Prochaine station, Legion.
account එක මල්ලිද දන්නේ log වෙලා ඉන්නේ කියලා මට හිතාගන්න බෑ. ගන්න ඕනේ ගන්න. ඒව ගේනවා ඔයාලට. ඔව් කැනඩා ඉන්නේ. හරි අම්මේ. පරිස්සමින් එන්න. මල්ලි මං කිව්වේ මල්ලි නෙවෙයි බං. නෑ අම්මා නම් ඔච්චර chat කර කර ඉන්නේ නැහැ. මල්ලි වෙන්නේ. Hello. ගියාද? දැන් හරිද? අයියෝ තෙල් ඉවරයිනේ.
Leitrim Station. Station Leitrim.
අම්මව ටයිම් අවුට් කරාද ඔයාලා? අයියෝ. මම දැක්කා. හොඳින් ඉන්නවා. පුතේ දැන් එන්නම්. ඔව් එන්න. තව විනාඩි 8යිනේ.
Southbound to Lineback. Direction Sud. Lineback. Next station, Beausville. Prochaine station, Beausville.
Sorry පුතේ. වැරදිද කවුද යකුසල් ටයිම් එකක් දාද?
Station Munsell.
ඕ පන්සල් තියෙනවා. පන්සල් 3ක් තියෙනවා ඔටාවල. ඉවරයිද? gift කරා. උදේ gift කරානේ 10ක්.
Attention! The next Line 2 train, northbound to Wilting, is departing from platform 2. Attention! Le prochain train de la ligne 2, en direction nord vers Bayview, va partir du quai 2.
Siya game nagagahiti mo hitan. Ilat ka muna daw. Hari. We are on the way. Okay. Ayyo, mata screen nagapin. Sitalai. Natural ke sitan. Petak. Lagi. Ya tahu macam lagi. Chat lagi.
Tuh tengok keluar ada aku. Ini mama mali nih, ini mana nih?
Oh ya di itu.
Ayo. Bukan dane mama.
Itu tarah mula tapi.
Tarah mula tapi mau kuda? Ayah nih mama nih kira kiu.
Ayo. Oh ya di.
Oh ya nih mama nih kira oh ya nih kiu.
Ini ekadika me ya nih bagi dalin nagat.
Ada mata dari dia. සද කවුද?
ඔයාව ටයිම් අවුට් කරා. අයියෝ.
මං යාව ටයිම් අවුට් කරා විනාඩි පැය භාගයක්.
මේ නංගි.
මං යාව ටයිම් අවුට් කරා පැය භාගයක්.
ඕ නා අම්මා ඉඳලා තියෙන්නේ.
අයියෝ
අනිතේ මාදිකේ.
මල්ලි දන්නේත් නෑ. මල්ලිගේ account එකට බලන්න. අංගා හිතුව මල්ලි වගේ ඇක්ට් කරනවද කියලා තියෙනවා. ආ හිත නෑ. ඕනේ නෑ. එනද මං කියලා කියද්දි කැදි මල්ලිගේ කියලා.
අනේ නෝයයි කතාවේ විදිය මල්ලි බොරු කරනවා කියදන්නේ.
ඈනේ මං ඇහුවානේ වෙලාව කියන්න කියලා ඊට පස්සේ මං WhatsApp බලන්න කියලා WhatsApp කියලා දැම්මා.
ඔව් මං දැක්කා WhatsApp notification එක ආවා.
අද කොහමද?
ඒ මොකද ආයේ එහෙනම් එක්ක අහිනවා. අපේ ලයිව් එක තාම අහගෙන ඉන්නේ.
ඇයි නංගි දාගෙන නැත්තේ?
මේක සද්ද. මට එුණනේ කහිනවා.
ඒක සද්ද දෙන්නේ බබා. මම මේකට චෙක් මෙයා වෙලා තියෙන සෙට් වෙලානේ තියෙන්නේ. Bluetooth.
මන්න රැවටුණාද මල්ලි කියලා. සසිය කියලා. දැන් අතන chat එකේ සාතු මිනිස්සු හැදිලා වගේ හිටියා ආච්චි වැහිලා වගේ මන් තමයි අම්මා මම ඇටි
එහෙම කියලා දැන් කතා කරන්නේ
6 වෙද්දි කරුවද නැද්ද මේ සමයකේ
දැන් සුදු පුතේ
වෙන කොහොමද තියෙන්නේ වින්ටර් එකේ ගොඩක් කලින් මොකද කියන්නේ
ඒක දැන් කියන්නේ
වෙනකම් උදේ
අද ලංකාවේ දැන් බදාත නිවාඩු දිනක් කරලා තියෙන ලංකාවේ අද නිවාඩු.
ඔව් ඒක තමයි තෙල් නිසා මම දැක්ක මිනුවය දාලා සුදු පුතේ කිව්වේ මට දිගේ දාලා.
කවුද දාන්නේ?
සෙසි බොට්.
ඔව්. ඔයාට තමයි සුදු පුතේ. ආයෙත් බලලා තියෙනවා ගෙදර ලොකේෂන් දන්නවද?
ඔයා නිකන් සුද්දෙක් වගේ ඉන්නවලු.
කවුද?
ඔයා.
ඇයි ඒ?
ඇයි කියලා දන්නේ එහෙම දාති.
කවුද දාන්නේ?
සිත්තු කියලා.
අනේ නෑ මං එහෙම නෑ. මං එහෙම නෑ. මං එහෙම කෙනෙක් නෙවෙයි.
නංගි වගේ සෙල්ලම් බඩු පෙන්නන්න.
පෙන්නන්න ඉතින්. කො පෙන්න ගෙනාව නේද එකම?
මට ඇහුණා.
අනේ ගෙනත් තියෙන මට ඇහුණා. බොරු කියන්න එපා. බොරු කිව්වහම පෞසිට වෙනවා. බොරු පොඩ බොරු කියන්න පුරුදු වුණාම ඇත්ත කතා කරන්න නම
ලංකාවට වැඩිම නිවර්දිනට ඔව් ඇත්ත. මම හිතන්නේ තුන්වෙනි ස්ථානෙට තියෙනවා ලංකාව. කියනවලු. මොකද අම්මා සුද්දෙක් වගේ ඉන්නව කියලාද?
ඈ?
නැත්තම් සුදු පුතා කියලා. ඒක පස්සේ නෑ සුදු පුතා කියලා. මෙහි පෙට්‍රල් ලීටර් එකක් කීයද කියලා අහනවා.
පෙට්‍රල් ලීටර් එකක් දැන් නම් ගණන් ගිහිල්ලා තියෙන 1.50 ගණන් කියන්නේ ඩොලර් 1යි.
මොවයි.
ඩොලර් 1.50 ගණන්. ඩොලර් කියන්නේ කැනේඩියන් ඩොලර් නේ US ඩොලර් නෙවෙයිනේ. ටයිම් බෝම්බයක් තියලා තියෙන්නේ. ටින් ගාලා
පුපුරන්න යන්නේ. නංගි කියන ඇඩ්‍රස් එක පෙන්නන්න එපා කියලා.
ඈ?
නංගි කියන අපේ ගෙදර ඇඩ්‍රස් එක පෙන්නන්න එපා කියලා.
ගෙදර ඇඩ්‍රස් එක? ගෙදර ඇඩ්‍රස් එක පුළුවන් නම් හොයාගන්න කියමුද? බලන්න චැලෙන්ජ් එකක් දෙමුද? හරි පාර හොයාගන්න ඕනේ කියලා කියමු. හරිද? දැන් පාරවල් ගහලා තියෙනවා මේ දෙපැත්තට. හරිද? පාරවල් ගහලා තියෙනවා කොයි පාරද කියලා කියන්න. මං ඉතින් ඒ පාරේ
නෑ වෙන දෙයකට නෙමෙයිද අම්මා සුනයි කියලා.
සූත්තිය ලස්සනයිද පුතේ? සූත්තිය ලස්සන නෑ ලංකාවේ අයින ලස්සන. දැන් ඔය දැන් චැලෙන්ජ් එක බාරගත්තද? පාර බාරගත්තද චැලෙන්ජ් එක? කවුරුත් බාරගත්තේ නැද්ද?
තාම ඇහුන්නේ නැද්ද මන්ද? ටිකක් පොඩි ඩිලේ එකක් තියෙනවා.
නවත්තන්නද?
නෑ උන්නේ.
ඇහුණාද?
අපි මොන හරි එවන්නම්.
ඈ? අපිට වෙරළුද? හරිද? කවුරුත් චැලෙන්ජ් එක බාරගත්තේ නැත්නම් යන්න දෙන්න.
යා.
අයියෝ. අපි සෙනෙසර් මැසේජ් කරලා අහන්න බෑ කවුරුවත්. හරිද? හලෝ පාර බලමු. බාරගත්තේ නැහැ?
පුළුවන්ලු. ජිය ගැස ගහන අපිට මේව ඊසි වැඩලු.
හරි ගහලා කියන්න එහෙනම්. කියන්න ඇඩ්‍රස් එක.
තටියක් හයියෙන් යන හිමියන වැඩි වේ.
ඒගොල්ලන්ට පේන්නේ.
දෙච්චර දේසි කරදි වැඩන්නේ.
පාර කොයි පාරද?
උනේ.
එතන තියෙන පාරවල් ගොඩක්. කොයි පාරද හරවන්නේ? කොයි පාරද හරවන්නේ? මේ පැත්ත පෙන්නන්න ඕනේ ඉතින් පාර පෙන්නුවේ නැත්තම්.
දැක්කයි ඉතින් සයින් එක පේන්න තිබ්බා.
කියව ගත්තද?
දන්නේ.
ඕකේ. දැන් දන්නවනම් ගෙදර නම්බර එක කියන්න.
අපි පෙන්නන්නේ
කවුරුත් දන්නේ නැහැ වැඩක් නැහැ. ලංකාවට එනකොට මොනවත් අරන් එන්න වැඩක් නැහැ.
ඇයි දවසද මුණග නැත්තම් හොඳයි. බාරගත්තලු චැලෙන්ජ් එක.
බාරගත්තා? කී කොයි ඉතින් ගෙදර ඇඩ්‍රස් එක?
වමට තාම ඒගොල්ලන්ට මේ අපි අතන ඉන්නවා. මේ මොකද අපේ ලොක් අපේ රෙඩ් දාලා.
අනේ සෙනුලි අරින්නකෝ ගහනවම දැන්.
මම මේක ලොක් කරේ නෑ. අන්න තාම යන් හයියෙන් වමට තාම ඩිලේ.
තාම ඩිලේ. දැන් අපි ගේට් එක ඇවිල්ලා කියලා තාම ඉන්නේ.
තාම
ලොක් කරේ නැත්ද? අස්සියන ලොක් කරා කියලා හිතන්නේ.
නෑ එන අල්ලගෙන හිටියා. නෑ මං අල්ලගෙන හිටියේ නෑ මම මෙහෙම හිටියේ මං ඒකයි දොර මෙහෙම කරේ. මං අතරම ලොක් කරේ නෑ. I just weak. Weak.
Nothing happened.
අනේ නෑ නැන්ද සුද්ධිය ලස්සනයිද? Can I see something? Can I see? Wait, what? I think මං අල්ලන්නේ. No, it's hard. What? No. Give me hard. No, you have a good. I pinky promise. I pinky promise. I pinky promise. Wait, I want to see it. I want to read. Why do they have? Go in there. Wait, I want to see something. Tama, cute. What do you have? I'm doing it. I'll take it over there. Are you got it? Because I'm very nice. Very nice. I promise. Mandagata. Jacket Wait, I'm hello again. Wait. Hello. Good evening. Can you please please? I'm then chat again. මේක දැන් ලෝඩ් වෙන එකකින් දෙපයි නැත්තම් එන්ඩ් කරන්න බෑ. එතකොට ඒගොල්ලන් බයි කියන්න ඕනේ.
තාත්ති උඩ.
Wait, I could take it upstairs. I might have more. මම එන්න කරනවා දැන් තාත්ති එක. එපා ගන්න. I might have more internet upstairs. ඉන්ටර්නෙට් එක ගන්න නෙමෙයි දැන් තාම ලෝඩ් වෙනවා පරණ ටික. හරිද දැන්? සිග්නල් නෑනේ. මොකද ඊ බලන්න මේ ෆෝන් එකකින් ඔය කලින් බලන් හිටිය වගේ ලයිව් එක ඒගොල්ලන්ට තාම මොකක්ද දන්නේ නැති. No thank you. Okay. මම බලන්න. Okay. Can you do that for me? Please. Why not? Why not? Why not? Why not? Wi-Fi. There you go. By the way, going to get down here. Oh, I can hold it. No, it's okay. Oh, I actually want to take it. Okay. I promise I won't take it. I promise I won't. It's okay. Why does it look like that? Right. Then get the rabbit a more leg. Look at it. Data down. Then get it. අපි යන් ගිය ඇතුළට
ඒ ඇතුළේ තමයි.
නෑ මං කියන්නේ තව ඇතුළට. Hello. Signal. Let's
go upstairs. Let's go upstairs.
මේ පේන විදිය ලයිව් එක කට්ටියට.
මොකද?
දැන් හරි.
නෑ ස්ලෝ කියලා කියන ලස්සන ස්ලෝ
Still there.
අයියෝ. Check the main beam.
That's very slow.
Oh, here the copyright is done. TV केवल. अभी मित्र को चाहिए बाहर. Let's go upstairs.
අපි ගේට්ටු තාම දෙන්නේ.
තාන්නේ?
නෑ මම කියන්නේ.
මානද ගියම ගේට්ටුට ඇවිල්ලත් හරියන්නේ නැහැ.
වගේ දැන් ඔෆ් කරලා ගන්න දැන්.
මම දැන් wifi ඔෆ් කරලා data දැන් අම්මෝ බහැලා වුණත් මේ ඇයි?
හරිද? කනෙක්ට් වුණාද? රීකනෙක්ට් වුණාද?
හරි.
රීකනෙක්ට් වුණා.
අයියෝ ලයිව් එක. අන්න අපි උඩට ආව දැන් ගොඩ වෙලාවක් තිස්සේ අපි බලන් ඉන්නවා. පොඩ්ඩක් chill. No. I want to make the song.
අයියෝ දැන් නම් කඩරි දෙනවා.
සද්දේ මේ Discord එකේ රග්ගි සම්පූර්ණ ස්පෑම් කරනවා.
විස්සක් ඉන්නාර 12ට කොහමද ගන්න? 20? ඒකේ.
එන අපි ලයිව් එක දැන් එන්ඩ් කරනවා. එන්ඩ් කරන්න තමයි බලන්න හිටියේ.
ස්කෑම් යාද උනේ සෙට් එකේ. ස්කෑම්
නෙමෙයි. මම අද ලයිව් දැම්මා.
මේ මොනවද රුසියා දාලා තියෙන්නේ? මම ඩිලීට් කරනවා.
බයි කෙනෙක්.
No.
නංගිනා අපිට කන් දෙකක් තියෙන. නෑ නංගි නවත්තන්න එපා.
Yeah. නෑ සම්පූර්ණ එක නවත්තන්න.
නංගි මගේ කන් දෙකේ හින්දා.
එන් කරනවා. සිග්නල් හදාගත්තේ එන් කරනවා. What? You love saying that all the time. Yeah, you do. You're always like that every single 5 seconds. I know. Oh! The net.
Yes, Nagi, yeah.
Bye.
After the best song in the world. It's the best song.
No.
Bye.
Bye. Sanai. Khata karlo chat ke. I don't want to go bye.
Mama done.
I don't want to go bye. Bye bye. Bye 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 bye. ඊළඟ live එකෙන් හමු වෙමු. Yay! කවදද දාන්න කියලා කියන්නේ නැත්නම් scam. I'm gonna always be on way I can because I don't have Discord. I don't have Discord.
Nangi fa kiyanne. Nangi ekkan fa.
Bye Dian. Bye Dian.
Bye. Fa.
Kamera wahan lagi atin. Bye.
ෆෝන් එක කරන් දුවගෙන විසි කරන්න එතකොට එන්ටි කළා අම්මා
කැඩෙනවා.